A little bit of a review of what, oops, that's not what I wanted to do. Where is the little button? Oh, there's right there. Let's do a little bit of a review of where we were, okay? If we looked at this reaction last time, this slide, and we identified the, well, actually we didn't get to this one, I don't think. Or we didn't talk about that. Here's where we were, right here. Okay. We looked at this reaction last time, identified the intermediate in this reaction, and Camille, if you can look at this reaction, and maybe your notes if you want to. Do you remember what the intermediate for this reaction is?
Is it the IO minus?
The IO minus. Now, how is it that you're going to be able to pick out the intermediate when it comes time in the exam? How did you do that?
Well, if I'm going to be honest, I just remembered it was the IO minus from last class.
Okay. All right. So the word intermediate kind of means in the middle, right? Temporary, doesn't last forever. It's kind of just transient. And for chemical reactions, intermediate means something that's not in the beginning and not in the end. It appears and then disappears, right? So if we can look at these steps in a reaction, and when you see something like this where it says slow and fast, these are steps in a given reaction, okay? The overall reaction itself would be the sum of all the different steps of the reaction, right? And we wrote this last time. In fact, I think I have it right here. If I take the steps for this reaction and I add them together, then we can see first step, second step, the overall reaction is this 2 hydrogen peroxides going to 2 waters and an oxygen, because these cancel out, right? So when we're given when we're given microsteps or steps in an overall reaction, these steps don't necessarily indicate this is not the reaction, step 1, and step 2 is not the reaction. These are steps of a single reaction, right? But from them, we can look and see what kinds of chemicals don't start at the beginning and kind of just appear as products for some of the other steps, and then they're gone by the time we get to the end. So that's how we can identify the intermediates. Does that make sense, Camille?
Yes. It's a lot of information.
What's that? Okay. So,
There's a lot of information.
well, why don't you explain it to me? How can we identify the intermediate in a reaction?
I really need, I know you just explained it, but I'm struggling.
Well, that's fine. I just need to explain it a little bit more succinctly, probably. Do you understand that these are only steps in the reaction, and that if I want the actual reaction, I have to add them together? Does that make sense?
Yes.
Okay, great.
So like the first, yes. Okay, yes, that makes sense.
So in these steps, we have different species, right? We have 4 different things showing up here, maybe 5. Which one of these species would not be in the overall reaction, though, because they get canceled out, Camille?
The IO minus.
The IO minus would not be. You see, it's on the product side here, and it's in the reactant side here. Anything else?
The I minus.
The I minus, that's right. So that would tell us that the IO minus and the I minus would be good possible candidates for our intermediate, right?
Yes.
But the word intermediate means it's never there in the beginning, it's just in the middle. So that would rule out which one then, Camille?
The H2O. Oh wait, no, just the IO minus.
It would rule out the I minus, right? Because it's apparently in the first step you start with H2O2 and I minus. Okay? So because I've put this into the container to start with, it's not an intermediate. It doesn't appear in the middle of the reaction. It's there in the beginning. So that's how I would know that the I minus is not an intermediate. But the IO, it just appears from the first step and then it's consumed in the second step. That's how I know that the IO minus is an intermediate.
Intermediate.
All right. Now, what do we call I minus? I minus is there when we start, and it's there when we end. But apparently, it looks like for the first step to proceed, it's necessary, right? And also, it's contributing in the second step through the IO minus, right? So what do we call that? That's called, it's a chemical or material that helps the process proceed, but in the end, it doesn't disappear. It's still there. A catalyst. That's right, a catalyst. Okay, so we can identify the intermediate as something that appears in the middle of the reaction, but is not as a product. We can identify the catalyst as something that is placed in the reactant, but never gets consumed during the reaction. In the end, it's still there. All right? And the rate determining step is always going to be the which step, Sarah?
The slow step.
The slow step. That's right. The slow step. And the way that we can kind of visualize that is if we have kind of an energy diagram showing how the reaction proceeds versus time down here, and we have our energy on our y-axis, okay? We start with our reactants. The reactants proceed to interact with each other, collide, and there is an activation energy, an energy that needs to be overcome before those reactants, and I'll draw the reactants as little kind of billiard balls here, they have to combine with enough energy, and this is the amount of energy necessary, before they'll form and they'll do any chemistry, right? And so once that occurs, according to these steps up here, it says that our IO appears. This is where our IO is. That's an intermediate. And then after that, another portion of the reaction has to occur. Okay? Another portion of the reaction has to occur. But because this one is the slow step, it is the one that requires the most energy to overcome. By the time the materials get past this, they have enough energy that they'll easily be able to sweep past the second step. So that's why the highest activation energy step will be the rate determining step. It'll also end up being the slow step in the reaction. Okay, so that's how we can determine our rate determining step. And then, as I mentioned here, this represents the presence of an intermediate, a valley in one of these energy diagrams. Okay? All right. So that's a little bit of a review to catch us up to where we were. Now we want to talk a little bit more about what we can glean from this stepwise information, or this mechanistic information about the mechanism. All right? The observed rate law, now hopefully you guys remember what rate law means. Rate law is that thing where we write the word rate, it has K, and then it's dependent on the concentration of some reactants raised to an exponent, right? That's what rate means. And the observed rate law will usually match the rate determining step, which means it will usually match the slow step. And that's because the step that governs the rate, whatever process is necessary for that step, that's the one whose concentration will influence that specific step. So we can look at a chemical reaction like this then, and we can create a rate law from simply this mechanistic information. Now, I told you last class, and the one before that there's only one way to determine the rate law. And the answer to that, Alyssa, do you remember what is the one way to determine the rate law?
Or experimentation.
That's right. Experimentally is what we said, right? Or by experimentation, you can determine the rate law. Now, there's no way you're going to have received any of this information without performing lots of experiments. You don't know the stepwise process for a reaction without doing lots of experiments. So in the same, in that, from that perspective, it's still the right answer. But once somebody has performed a lot of experiments and identified the slow step, so here's the slow step for the reaction, we can get a general rate law from that information. So we can say that the rate of this reaction will be K. I mean, we don't have a value for K, but we know it's going to, the rate is going to depend on the rate limiting step. So the rate limiting step for this one is rate K, concentration of hydrogen peroxide. And then because this is the rate limiting step, then I can use the stoichiometry on that hydrogen peroxide as the order for that reaction. All right. Now, we do need some more information about rate, the rate of any given reaction experiment to solve for K here. All right. So it doesn't get as much further than that, but we can tell the order of the reaction with respect to our reactant by simply looking at the slow step in the reaction. Okay. That being said, let's see if we can get some help with this one. Jace, do you want to help us out a little bit? Here's a chemical reaction, and they're asking us what is the expected rate law for this reaction. All right.
Would it be 2 because the slow step is in the second?
Okay.
The second.
So this question here is saying what's the expected rate law? And what you've identified when you said the second step here is that this is the slow step, therefore it is the step which will govern the rate. So this is the step in the mechanism that we have to use to identify the rate law. Okay? So our rate law will look something like rate equals K, and then what are our reactants that are going to be involved in the rate law? Maybe I drew too many boxes. Jace, what reactants should I put in these boxes?
C and B.
C and B? Okay. So I'll just do that for now, C and B, extra box there. Now, what about, what kind of component is C in this process, Jace? Can you tell?
It's an intermediate.
It's an intermediate. That's right. So it's not a reactant. So it's not going to be involved in determining the rate of the reaction because we just put in here to start, and there it is right there. I mean, here's the overall reaction. The overall reaction is just the sum of these two, right? Or these three. So all we did is put A and B in there to start off with. Okay? So the rate is going to be dependent on B. We know that because it's the slow step here. We're not going to include C because that's an intermediate. But what about the order with respect to B? Jace, where do we get that? Where do we get that exponent there?
Honestly, I forgot. I don't know. I think we're not supposed to use the coefficient or the moles for 3, right? Or is it going to be like 3? I can't remember.
Well, let's see. Camille, do you have any ideas? Our rate law right now looks like this. Rate, K, times the concentration of B. We know this much. We're trying to solve for this X right here. We know this much. We know this is our current rate law because we've identified that the second step is the slowest. Therefore, it's the step that's going to govern the rate of the reaction. We didn't include C. Do you remember why, Camille? Why didn't we include C?
Because it cancels out.
That's right, making it an intermediate. All right, so it was an intermediate. So only B. Now, how do I get this number? Do you know, Camille, how I get that exponent there?
We have to use the other step.
Well, actually, what we said was if you are given mechanistic steps like this and you know what the slow step is, you can just use the stoichiometry on the reactant of interest in that slow step. So that would mean X is equal to what then, Camille?
I need help. I'm sorry again.
No, that's fine. That's fine. So we're using the coefficient on B in this slow step. And so because it's just a 1,
3.
it's just a 1 right here though, right?
Oh, yes.
So it would be first order with respect to B. Okay? Very,
Question,
yeah.
to clarify. So we can use the stoichiometry ratios whenever they're split up into mechanisms?
That's right. When you have and that's the interesting thing about having mechanistic steps. If you have the mechanistic steps, then you can find the slow step, find the reactant that will be contributing to that rate law, and then use the stoichiometry on that reactant as your exponent in your rate law.
So if it was 2B, would it be like rate equals KB squared?
If the 2 was right here. Right.
Yeah, okay. Sweet.
That's right. Okay. Very good. Let's see. So, catalysts. What do catalysts do? And I think that you've probably heard about this before. I know that I heard about this a lot in other classes before I got to my chemistry class. But catalysts don't change the overall release in energy of a process. All they do, or what they, not all, it's an important component, but they lower the activation energy. They lower the activation energy. So let's look at a energy diagram for a reaction here. As the reaction proceeds to the right? Okay. We start off with our reactants, and our products, let's say, are going to be there. Let's see, Sarah, can you help me identify? Is this going to be a exothermic or an endothermic reaction?
I'm sorry, which ones were the products?
Products are always over here to the right.
Okay.
So here's our reactants.
So that would be a positive release. So is it endothermic?
Endothermic, that's right. That's an endothermic process. And we could put a number on here, on this one here, maybe like 10 or something. This one would have to be lower. Products minus reactants would equal a positive value. So that would be endothermic in terms of energy change. All right. And then if we had an activation energy associated with this process, the activation energy would be that change in energy there. All right. The overall change in energy is just products minus reactants. So this is my change in energy. But this is what we call our activation energy. So when you have a catalyst, you don't change where the energy for the products are or where the energy for the reactants are. You just make it easier for the process to occur by lowering the activation energy. So this one down here would be with a catalyst, right? And you've lowered your activation energy. Okay? So catalysts don't alter the products, reactants or products, but they just lower the lower the activation energy. Okay. All right, so let's have a conversation really quickly about how increasing the temperature of our reactants would change this reaction. All right, looking at the uncatalyzed reaction, if we increase the temperature, temperature is all about what, Alyssa? What are we referring to when we talk about temperature?
The temperature, like, that's being released by a reaction.
The temperature of the reactants. So if I have A and B in a pot and they're not reacting, but if I heat them up, what am I doing to A and B when I heat them up?
You're increasing the rate of collisions of the molecules. Therefore, like,
So let's the energy.
yes. Yes.
Camille knows all about this. That's right. The kinetic energy, we're increasing the energy that we're increasing the motion, the kinetic energy, how many collisions are occurring here. All right? And when the amount of collisions occur enough that the energy is such that they can overcome that activation energy, then the reaction will proceed. So temperature doesn't lower this, it doesn't change this, it doesn't change that. It just makes more collisions between A and B so that they'll have enough energy to react.
I actually have a question about that.
Yeah.
Sorry. So I was watching this lecture, and so you said that the molecules, they can go up the activation energy slope or whatever, can go up and back down, and until they reach the point that they come over it and can become the next, the reaction occurs.
Yeah.
Where does that energy go if it just keeps going back up and back down? Is that just the rate of motion? Is it just the kinetic energy that's changing?
That's right. That's right. So these things are colliding and transferring their energy to other things, other molecules, other surrounding, the conditions, whatever it is, increasing the temperature of those collisions. But unless the collision occurs the right way, the reaction won't occur, right?
Okay, thank you.
Okay. So that's what catalysts do. They lower the activation energy. And we have something that are called heterogeneous catalysts or homogeneous catalysts. A homogeneous catalyst is a catalyst that will be in the same phase as your reactants, whereas a heterogeneous catalyst like this here is a surface that can bind to, this is a physical solid surface that is binding to gaseous molecules of hydrogen and nitrogen. As the hydrogen and nitrogen is bound here, it makes it easier for them to react because they've been kind of trapped momentarily. And so when they're trapped nearby each other, they can react more easily. So this is an example of a heterogeneous catalyst. Different phase that will allow the process to occur more easily. And again, the catalyst at the end of the reaction isn't changed. All right, there's one other thing we need to talk about, and then we're done with this chapter. The last thing we want to talk about is what these progress curves, now let me remind you what a progress curve is for a reaction. A progress curve is when we take a chemical in a reaction, a reactant, A going to B, versus time. All right. Over time, what is going to happen to the concentration of A, Jace? How is the concentration of A going to change over time, Jace? What do you think, Camille? How's the concentration of A going to change over time?
It's gonna lower.
It's going to decrease. That's right. The concentration is going to decrease, get lower, right? The concentration is going to lower over time. Now, we talked about how the decrease might be linear, right? And if it's linear, that means that it doesn't matter how much A there is, the rate or the slope of this line is the same throughout the whole reaction. And we call that a zero order reaction. It's called a zero order reaction because in the rate law for this reaction, rate will equal to K times the concentration of A to the 0 power. Thus, the rate is equal to just a constant value. And no matter what the concentration is, you can put in any value here. Because it's raised to the 0, it won't alter the rate of the reaction. Now, if you have the rate of a reaction, same reaction, but if the reaction is first order, then the rate law will look like this, A to the 1, and as the material disappears, just like before, it will disappear, but then as the concentration of A goes down, the rate of disappearance will slow. The rate of disappearance will slow, and you'll get a slope that looks like that, or a line whose slope is constantly changing. All right? There is something interesting about this first order rate, this progress curve for a first order reaction. It has a special property that has to do with time. If this is time 0 and this is 100%, then there's something special about how much time it takes to reach 50% of the reactant. Do you remember what that is, Sarah?
Yes, is that talking about half-life?
That's right. So explain to us a little bit about what the half-life means. What does that mean?
Half-life is how long it takes for half of the material to decompose.
All right, good. So if I'm at 50% here and it took, let's say, 10 minutes, then how much time is it going to take for me to get down to, or where will I be at, let's say, after 20 minutes, Sarah?
You'd be at 25%.
25%. That's right. So an interesting thing about first order reactions is they have a fixed half-life. In other words, it's always the same. Regardless of the concentration, the half-life is always the same. Now, this is not a linear relationship like our zero order reaction is. And we like things to be linear in the lab, especially because when they're linear, then it's easy to predict where the concentration is going to be. It's also easy to predict where the intercepts are going to be, right? And we can do other modifications of data when there is a linear relationship. So because this isn't linear, there is something special that you can do to the data to make it linear. If you take the natural log of the concentration of A and plot that versus time, then you will get a linear relationship. A linear relationship. So this is only for a first order reaction, right? But in a first order reaction, you will have a linear relationship if you take the concentration of A and take the natural log of it and plot that versus time. All right? For a zero order reaction, all you have to do is plot the concentration of A and you'll get a linear relationship. But for a first order reaction, you need to plot the natural log of the concentration of A versus time to get a first order reaction. All right? Now for a second order reaction, you get something like this, where the rate of the reaction is equal to, here's my reaction again. We put two A's there this time, because the rate of this reaction, now don't get confused, well, I won't put that there. That'll confuse you. Rate of the reaction here is some constant times the concentration of A raised to the second power. This is a second order, O-R-D-E-R, reaction with respect to A. And what do you think? Whose turn is it? Alyssa. How is the second order reaction's concentration of A versus time, how is it going to differ than compared to a first order reaction?
Well, I think it's going to decrease at a higher rate because it's being used at a higher rate.
Okay, it's going to decrease at a higher rate because it's being used faster. But then you also have a sharper inflection, because as that concentration goes down, the rate is more dependent on its disappearance, right? So you get, and here's kind of a professional drawing of all three of these that we've been talking about. If you plot the concentration of time for a zero order, concentration of time for a first order, and concentration of time for a second order. Okay? And if you try to look at the half-life for the second order reaction, the half-life will differ depending on the concentrations, right? And then what we're seeing here in this small little, whoops, what did I do there? This small little section here, this area here, is, again, if we plot the concentration of A versus time, we get a linear relationship. If we plot the natural log of the concentration versus time for a first order reaction, that's how we get a linear relationship. And on this second order one, we have to plot 1 over the concentration versus time. And now when you do 1 over, the slope is going to go an opposite direction, right? But this will be a linear relationship. Here, the slope of this line is equal to K, the rate constant for the reaction. Here, the slope of this line is equal to K, the negative slope, sorry, for both of these. The negative slope is equal to the K for this reaction, and for the second order reaction, the slope of this line is equal to the rate law for that reaction. All right, so those are all the different things that we want to know about kinetics, right?